Hello and welcome back. We have previously discussed how we can use machine learning to classify damage in dual-phase steel, and now we want to start looking at the technical details and the implementation. So we load the relevant libraries. We have our custom utils, the clustering algorithm that we have discussed why we needed previously, and we use Keras from TensorFlow. So first of all, we set an image threshold because we previously said damage sites are associated with dark regions in the electron microscope image. We initialize a dictionary that holds all damage sites that we have found and load the image. There's an example image in this repository that we load, and then we can use this to look at it and see what we would expect. So we can see that there are a number of obvious inclusions because they have such large holes in them, and then at this magnification we can't quite see all the damage sites that occur. So in the first step we need to find the candidates for the damage sites. So we set our threshold in which we say that the pixels belong to a potential damage site here. Right? So this is how we do this. We can look at what this does. And then we can run the clustering algorithm. This is in a separate file, we'll discuss it separately, and it returns us a list of all XY coordinates of the centers of clusters that we want to consider further. There are two corrections being applied. It can happen that some pixels inside a cluster are above the threshold due to random fluctuations. In order to minimize this, we can fill these small holes inside. And sometimes we may essentially find the same cluster multiple times. So different clusters are found by the clustering algorithm, but they're essentially the same damage site. So this can, for example, happen for inclusions which are much larger, and we want to filter these out so that we don't have the same damage site multiple times. So we run our clustering approach to get the centroids, and then have this as this return variable. So we have now the number of damage sites we want to consider further from this example, and we identify 51 of them. What we can also do, this is another helper function that we write in our utils. We can draw little boxes around it to see where we spot them, and we've already included a legend that color codes what kind of damage is there, and black for no damage. And here, of course, everything is black because we haven't classified anything. But you can see that we already see those spots. Now we run the first model, inclusion versus the rest. The model is pre-trained and we simply load it. This is what we can do here. So it has a window size of 200 by 250 pixels, and we use a threshold of 0.7 and load the relevant model. This is what it's done. So we have an inception network as a base, and then the dense layer, this is what we have customized because we only have inclusion versus the rest. Before we run the network, we need to crop out all of these predefined window sizes around each cluster center, so all around these 51s, and put these images into a list that part of the network to operate on. So this is what we have in this helper function prepare classifier input, where we pass the image in, the location of all potential damage site, and the window size. And what we get back is then this variable that holds all of those, and we can, for example, look at this specific randomly chosen example. You can see, okay, there's a damage site here in the middle plus the window size around it, and just by looking at it you will probably say this is not an inclusion. Now we run the first network and we pass all of those into the first model. It runs, right, and then we can print a few of those predictions, and you can say inclusion versus the next, so we get two numbers out. Now we filter out all the damage sites that are classified as an inclusion, so we apply our threshold. Right, so inclusions here, this is the prediction, and now we modify this where this threshold is applied, where this 0.7 value occurs, and then np-where from the NumPy library gives us only those back. And then if we look at it, we have 5 inclusions as potential damage site. So we look at them, for example, the first one, and yes, that is probably an inclusion because it's a fairly large hole. Now we have this dictionary with all the damage sites, so we update this. Now we have everything not classified, so everything now that passed our criterion, the threshold, gets now labeled as conclusion. So we modify our dictionary and put the boxes with the respective color there. You can see that, we found 5 inclusions, and already at this scale that looks reasonable. There's a small one here that is probably missed, but we will need to investigate this further. Now we run the second network for all the other damage types. Essentially do the same thing. We remove first the items that we have already classified from the damage site candidates, and now this network has a smaller window size because the damage size is so much smaller. Now we have 100 by 100 pixels and a different threshold. Again, we load the model. You can see this is now a customized model specific for this application. But the overall logic is the same. Prepare the input, and we can look at an example again. And so we have 46 remaining because we already identified the inclusions. Now we run the model in the same way, but now if we look at the output, we see that we have more numbers, and this is because we don't have 2 classes, inclusion or not, but we have now the other classes, the ductile classes like Martin-Kraken, interface, decohesions, and so on. But the logic stays the same. We look at the threshold and take the one with the highest value. This is our class assignment, and the code does that for us. We have identified now 39 and not 41, so that for some of them the threshold is not reached. That means that the network is not confident enough that it has identified the correct damage type. So this is why we have a few black boxes left. And then we can see that if we update our plot with the colorful boxes, that we have now identified most of the damages that we have created earlier, in the sense that the clustering algorithm has found those points where damage is likely to occur. And now we would have to either use this result in our further analysis, or if we're still optimizing the networks, we would need to look at all of those in detail and see if the assignment